Today we are in Chapter 11, Section 2, Simplifying Radical Expressions. So we have already worked with radical expressions in last year and earlier this year. So who can recall what makes a radical in simplest form? Somebody give me a radical expression. I mean, give me a number. Any number? 2. Okay, so is this a radical in simplest form?
Yeah.
Is there a way we could simplify this? In radical form? You could approximate the value of square root of 2, right? But could you simplify it and it would still be in radical form? Or is it simplified? It is simplified. So how about this? If we have the square root of 8, is there any way to simplify that? Ryan? You could pull out a 2. So really, you're inside of that radical, you are factoring. You're saying there is a, what kind of factor in there? A perfect square. We know that in 8, we have 4 times 2. And so one requirement of a radical in simplest form is that we pull out any perfect square factors.
Isn't 1 a perfect square though?
1 is not part of our prime factorization, is it? Because 1 is not a, what kind of number? It's not a prime number. We could pull out 1s all day long. We could do 1 times 1 times 1 times 1, forever. And so when we are factoring, when we're doing our prime factorization, we're looking for prime numbers, okay? So no perfect factors inside the radicand. A second important feature of a radical in simplest form is you may not have a fraction in the radicand. And that's because if you have a fraction in the radicand, you will have a radical in the denominator, which is not considered simplified. You may not have a radical in the denominator. We're going to work with operations and radicals. So starting with the product property of radicals. We know that if we have the square root of AB, we could write this a different way. We could kind of expand this, right? And the square root of AB equals what? The square root of A times what, Anderson?
B.
Well, I don't know what you're saying. We could write it as a square root of A times, we have to say the square root of B. Good. So this works both ways. I could have 2 radicals that we are multiplying, and I could bring both of their radicands together under one radical. See that? Or we can factor things out and show 2 different radicals that are being multiplied. So we're going to work with that today. So an example could be, actually not an, we'll do an example in a moment, but what if we have the square root of a number squared? Square root of a number squared, Bianca? So what do we say when we have a square and a square root all in one expression? What kind of operations are those? Does anybody have the word? What are those? Lauren? Squaring and square rooting? Zach?
They're inverses.
Inverse operations, right? So we could say the square root of a squared is a. It's just simply a. Good. For this lesson, if you see a variable in the radical, part of the radicand, then assume it is not negative. In other words, in our previous example, here, if I see the square root of a, we're going to assume that that is a non-negative number. It is not negative, okay? Because that would raise a whole other issue, wouldn't it? Taking the square root of a negative, we know we can't do, so we're going to assume that a variable in the radical is positive, okay? So you don't have to write that, but you should know that. It says assume any variables in the radicand are non-negative. So let's use the product property of radicals, which is what we were just talking about. Here we have the square root of 48. So you are being asked to simplify the radical. That is not the same as taking the square root of 48. You all are really good at taking the square root of non-perfect square stuff. I mean, the square root of 48 is really close to what perfect square? 49, right? The perfect square is 49. And so your estimate is something different than simplifying a radical. We are just simplifying this radical, not estimating this. The estimate would be some number close to 7, right? Like 6.9. Okay, you guys are really good at that. But sometimes we leave our expressions in simplified radical form. That's what we're doing right now. Okay, so we're looking in here for any perfect square factors. Who knows a perfect square factor in 48? And the goal would be to find the biggest perfect square factor if you could. If you can't right away find the biggest perfect square factor in the number, it will reveal itself eventually. So you just keep working at it. So what do you see, Jimmy? Okay, so 4 times what? 4 times 12. And what does 12 have in it? 4 again, right? So really, we could write this as 4 times 4 times 3. That equals 48. You said 4 times 12, but 12 is 4 times 3. So what was the bigger perfect square factor in this? 16. And you didn't have to identify it right away, but it's starting to reveal itself now. See that? We have 4 times 4 inside of here. And when we have 4 times 4 inside of the radical, what's the square root of 4 times 4? 4. The square root of 16 is 4, so we pull it out. We take out the base, right? The one factor when we have 2 that are identical. So our simplified radical form here is 4 times the square root of 3. If you were going to actually approximate the value of this, you probably would end up with 6.9 to the 10th place. But that's not what we're doing. We're just simplifying the radical. Okay? This one's a little easier, I think, in one way. We have the square root of 25x to the 5th. So what's the first thing you think could be simplified right here? There's a couple things. There's 2 types of factors. There's 25 and then there's x to the 5th, right? And so what can we say about the 25? What do we say about that, Riley? That is a perfect square, right? So we could do what? We could take out 5. I mean, we don't like to keep expanding things, but we could write 25 as that, couldn't we? And we're really taking out the base, again, 5. Taking that out of the radical. It's a perfect square factor. What about the x to the 5th? Is there a perfect square in x to the 5th? Somebody show us how we can find perfect squares in that number. Because there are. Ryan. Well, we could write x to the 5th as how many x's in all? 5, right? I mean, we literally could expand it out 5. 1, 2, 3, 4, 5, all inside the radical, right? And so what do I have when I have 2 factors that are identical? I have a perfect square. I have x squared right there. And I have a second x squared, it looks like, right there. So how many x's may I take out for each of these? 1 here and 1 here. How many x's have we taken out? 2. So we write that as x squared. Now, this final x doesn't have an identical factor partner, does it? So it stays in the radical. So your simplified radical form is 5x squared times the square root of x. Go ahead and try these. If you're at home, pause the video and then come back and see what we found here. What perfect square factor is in 24? Juliana?
4.
Okay, so 24 is 4 times what? 6. And so what we can now do is do what?
You can take 2 out of 4.
Take the square root of 4 and bring a 2 out. The square root of 4 is 2. Are there any perfect square factors in 6? What are the factors of 6? 2 times 3. Good. And neither of those are perfect squares. So your answer is 2 times the square root of 6. Okay. How about B? What can we do with B? Bailey. Good. Square root of 25 is 5.
And then we can go to x.
How many x's do we take out?
1.
1. So your answer is 5x. There is no radical left. That 25x squared was a perfect square thing, wasn't it? A perfect square product. Now this next one says 25x to the third. So this is different. But it's a lot like that first one we saw, right? Jimena?
Is it 5x times the square root of x?
Very good. 5x times the square root of x. So when we have 3 factors of x, we could expand that to x squared times x, right? And we were able to take out 1x. The square root of x squared is just a single x. And 1x is left behind. So again, when you have an odd number of identical factors, 1 will be left behind when you take the square root. Okay? Multiply radicals. So this is, again, using what we just talked about with our product property. When given the product of radicals, we just multiply and then we simplify. Simplified radical expression is our answer. So square root of 7 times the square root of 7 is expanded, isn't it? We could kind of shrink it down and put it all inside of one radical, 7 times 7. And we could write that like 3 different ways, right? We could write that as 7 times 7. We could write that how else? As 7. Okay, we could write it as 49, the product of 7 times 7. Or we could write it as 7 squared, right? So all of those ways. But really, what will the simplified form be? What is the square root of 7 times 7? It is 7. Square root of 49 is 7. And if they wanted you to take the negative root, they would place a negative in front of the expression in this case, okay? So if they wanted a factor here to be negative, they would put a negative in front of the 3. And they will do that. You'll see that. But right now this is positive, and then the coefficient here is a 1 out here, a positive 1. So we leave it as is. So this is interesting because we have a factor outside the radical and then we have factors inside. But they're all factors. So we may bring them together just like we saw with the product property. We may say this is 3 times what really is inside the radical. 3 times what? Who can tell me? 2. Good. B to the 4th. There's 4 b's there. There were 3 factors of b here and 1 here. So there's 4. So do we have any perfect square factors in this radical? We do. So Sabrina, how many can we take out? How many b's? 2. So we have 3b squared times the square root of 2. So we multiplied that, and now we need to simplify. So what perfect square factors can you pull out? Do you know, Isabella? Is there any perfect square factor inside there?
No.
Actually, there is. What is the square root of n squared? Is 1n, right? And are there 2 m's here? Okay, you could call this m squared times m, right? Okay, we'll rename it, right? So can we take any m's out? And you get how many m's out? Square root of m squared is m. Good. And the square root of n squared we took out. So what's left inside the radical? M and this, right? So 5m. So there's your simplified expression. Okay, we have the quotient property, so we've got division property of radicals. Let's see, how can I do this? So we have a fraction in the radical. The square root of AB can be expanded in a similar way as we just saw with the multiplication. We could say the square root of A over B equals, who can finish that? The square root of A?
Oh yeah, the square root of A and the square over the square root of B.
Over the square root of B, good. Remember that the radicand, this expression needs to be a positive value. And we may not have 0 as b. b may not be 0 because what would happen if b is 0? Undefined, that's right. We wouldn't have a defined fraction. So let's try it. So square root of 5 over 49, we can now expand, right? And so we say, or we can pull it apart, square root of 49. So what can we do with that? Can we take the square root of one of these numbers? Yes, which one? 49, right? So funny how you guys say 7. The square root is 49 there. So we pull out a 7 and there you go. Do we have a radical in the denominator? Nope, so we're good. Can we do anything with that square root of 5? No perfect square factor there? So we're good. Let's try it again. And Alana, what do you have?
I have the square root of 11 over g squared.
Good job. So the denominator, we could take the square root of. There was 2 pairs of d factors, so we could pull 2 d's out. There's no perfect square factor in 11, so we stop there. Okay, let's try a few more, and pause it if you're watching by video, come back and check. There you go. Excellent. Okay, so let's try this final little concept today, rationalizing the denominator. This is called rationalizing because we have rational numbers and we have irrational numbers, right? And so if we have, what is an irrational number? Give me the definition of an irrational number. The largest group of irrational numbers are what? What group? I mean, it's obviously related to what we're doing today, right? So what is that huge group of irrational numbers? Ryan? The square root of a non-perfect square. So the square root of 2, the square root of 3, the square root of 5, the square root of 6, the square root of 7, the square root of 8, the square root of 10. We skip over the perfect squares. Okay? So we say that if we have a radical in the denominator, we have an irrational denominator. So we want to rationalize the denominator, make it a rational number that we know everything about. So how can we do that here? We're going to learn it now. Square root of 6 is not a perfect square factor. And so what could we do to the square root of 6 so that we can get rid of that radical down there? Now, we're really blowing up a fraction here. And the question is, what can we, when we blow up fractions, we get an equivalent fraction. It has the same value, but it looks different now, right? So we're blowing it up. And so the question is, what are we going to multiply the top and bottom by so that the radical is gone? What's the easiest thing to do to a square root thing in order to get rid of the radical? Square it, right? And so what would we multiply the square root of 6 by to get rid of the radical?
6.
The square root of 6. Good. So if we're going to multiply the bottom by this, we must also divide the top by that, because square root of 6 over square root of 6 equals what? 1. We're just blowing it up by a factor of 1, a special factor of 1 that we need to get rid of that radical. Okay? So in the numerator, we combine what we see and we have 7 times the square root of 6. In the denominator, we now have square root of 6 times the square root of 6, which is a square root of what?
36.
Which is 6. So there you go. You have rationalized it. In this expression, we have an irrational denominator. In this expression, we have a rational denominator. We know everything about the number 6. So it's rational. Okay, so go ahead and rationalize this one. Because you've got to factor out the perfect square factors, right? So what are you multiplying top and bottom by? Square root of 5a, square root of 5a. So what do you have? What did you get when you did this? Sabrina?
I got the square root of 15a over 5.
Good job. Now, can we simplify this? Anybody? Can we simplify it?
Yes.
What could we call it?
You can call it 3. No,
Could we do that? Could we? We really cannot. Okay, so I had to say that though because it would be so tempting to divide 15 by 5 and a by a, right? So I'm sure on a multiple choice test, they would have something like this available as an answer. No, 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 no. No, because this is not in a radical and this is in a radical. You may not bring an irrational and a rational all together. Okay, like that. Now we're going to just do a simple, it's not really simple. This is addition and subtraction. And as I've said before, addition and subtraction are often more difficult than multiplication and division. They truly are. They're more confusing. So hopefully they won't be if we talk about it. If you have this, where is it? Here.
Is this our last one?
This is it, the last section. We are looking at these terms the way we would if they had a variable. This is 7 square roots of 14. This is how many square roots of 21? It's 1 square root of 21. And this is negative 4, what? Square roots of 14. So which ones are the like terms? The square roots of 14 terms. This one and this one are like terms, right? So we can bring like terms together. I have 7 square roots of 14 minus 4 square roots of 14. How many do I have now? 3 square roots of 14. And I still have square root of 21. Now, square root of 21 feels related to the square root of 14, but they are not the same thing. And I know you could estimate their value, but we are asked to leave these things in simplified radical form, so we just leave it like this. Are there any perfect square factors in 21? Or in 14? 7 and 3 and 7 and 2? There are not. So we leave it like this. You may not combine them together. Okay? And to prove that, I'm going to show you just a little example. Square root of 9 plus square root of 16. So what is the square root of 9?
3.
And the square root of 16? 4. So we know that the square root of 9 plus the square root of 16 is what? 7 when you do that, right? So you could not bring these two together. You could not say the square root of 9 plus the square root of 16 is 9 plus 16 in here. What is 9 plus 16? It's 25, right? So square root of 25, is that 7? No, the square root of 25 is 5. So you may not bring two radicals together for addition inside of the radical. You should not move. You have work to do. Try this one. Now, these don't look like you can combine them, do they? They don't look like it, but you need to say, can I simplify a radical here? Which radical can we simplify? Lauren? Where's a perfect square factor? 28. What factor is in there? 4. The square root of 28 is 4 times 7, like that, right? So what could we call that?
You could say 4 square roots.
So we could, I'm just going to bring this down. 2 square root of 7 is this one, right? Plus, we now have another 2 square root of 7. So now we do have like radicals. And 2 square root of 7 plus 2 square root of 7 is 4 square root of 7. Okay? So you simplify, and then if they have like radicals, you may consider them like terms and add them or subtract them. Okay? We don't have time for that, so here you go. Here's your assignment.